Hey, AP Chemsters. Hopefully I'll finish up section 9.6 in this segment. We left off at problem 14. If you look at your notes, really most of the notes that are left are problems, at least with this section. So let's look at problem number 15. Order the following bonds according to polarity. You can look at your electronegativity chart. You won't always have those numbers with you. So how will we approach this without? Well, I noticed that everything's bonded with hydrogen first of all, and a couple things stand out. Look at the very first one, the HH bond. Is one hydrogen going to love electrons more than the others? No. All right, they're equally sharing. So that's going to be your least polar. Okay, so I'll put that down first. Okay, so if it's your least polar, let's go ahead and put that here as your first one. And then what else do you notice? Whoa, I'm seeing some of these big fours. Notice that three of those are dealing with the big four choices. So you know those are going to be the most polar bonds. So the other one left would be the SH bond. So that's not as polar. Now, in the order of who loves electrons the most, which one has the greater electron affinity, electronegativity, we know fluorine loves it the most. So I'm going to put the FH bond way over to the right because I know it is the most polar bond. So which is my second most electron loving element? And I believe that's going to be your oxygen. So know that. So your OH is here, and then your ClH bond is in the middle there. Chlorine is tied with nitrogen as electron loving. So please know fluorine is the most, then oxygen, and then chlorine and nitrogen are tied. So if I were to ask you which bond is more polar, ClH or NH, neither one is. They're equally polar. Okay. Then it says determine what the type of bond is. All right. So the HH bond is nonpolar covalent, okay, because it's equally sharing. What about your SH bond? S is right below oxygen. I don't have that memorized, so really the best way to answer this question is we got to look it up. So if you look up the S electronegativity value on the page before, what is this, on page 11, you will see that S has electronegativity of 2.5. So I'm going to write that down. And hydrogen is just one of those that, you know, if you use it enough, you'll start seeing it's 2.1. Well, if you subtract those two, you end up with a 0.4. And according to our rule of thumb, that those two values are so close that you really can't say who loves it more. So because it's a 0.4, it also is a nonpolar covalent bond. Now, these other ones, if you're working with a big four, chances are good to excellent that they're going to be a polar covalent bond. So I'm going to label these as polar covalent bond, and polar covalent bond. And look at the second item that we had to do for problem number 15. It said if it is polar covalent, which those last three are, please write your delta signs, all right? So let's go ahead here. Let me extend the page. And so let's look at the ClH bond first. Well, which one loves electrons more, chlorine or hydrogen? Hopefully you know what chlorine is. It's one of the big four. So if it loves it more, the electrons are going to be drawn closer to it. Because electrons are negatively charged, it's going to put on a partial negative on the chlorine, leaving the hydrogen partially positive. You'll notice that the same thing is true for the oxygen. And the same thing is true, oops, I forgot the F, for the hydrogens. Okay? So hopefully that answered that question. Hey, let's turn the page. All right, to answer problem number 16, it says without using a chart of electronegativities, however, I would use a periodic table to answer this. So if you don't have a periodic table handy, get one out now. All right, hopefully you found your periodic table. So why is that going to be important? Because if you remember our rule of thumb, let's go back here again. Nonpolar are the same nonmetals or very close to each other on the periodic table. So if they're close to each other, chances are good, not perfect, but pretty good that they're going to be nonpolar. But what about nonmetal, not close to each other? So the further away they are, the more polar covalent they're going to be. Ionics, metal, nonmetal. So let's go back here again. So without using the chart of electronegativities, but please use your periodic table, predict which bond in each of the following groups will be the most polar. All right, so in other words, which ones have the electrons the furthest away from each other? Okay, well, carbon and hydrogen. Carbon's another one you probably ought to know is 2.5, and that's really super important when we talk about organic chemistry. We'll talk about it later. So those are kind of close to each other. And then the silicon is where? Oh, it's below the carbon. It's in the period right below it. And then germanium is below that. So of all those three elements, which ones are furthest apart? And you'll see it's the germanium hydrogen one. So I'll circle that. What about the next one? Notice that we're looking at bromine, but where's bromine? It's at the bottom. So in this case, which one is going to be the most furthest apart? And I think you're going to see it's the aluminum. Carbon, oxygen, silicon, oxygen. Which one's going to be further apart? Well, carbon and oxygen are in the same period. Silicon and oxygen are not in the same period, so let's pick that one. All right. And then fluorine and oxygen, oh my goodness, they're using the big four here. So this is where I said, okay, you got to know these numbers, all right? Fluorine is 4, oxygen's 3.5. Carbon, or chlorine, excuse me, is 3. So I know it said don't use the periodic table or the chart of electronegativities, but whoa, really the best answer is they're both the same. Okay, so I really can't answer that. But if I didn't know the electronegativities, I would say that one would be. Okay, why? Because they are further apart on the periodic table. But it just so happens using those particular setups, in reality, they have the same electronegativity difference, so neither bond is more polar than the other. Okay, so it says in problem number 17, we just have to know which one is more electronegative than the others. If their differences are greater than 0.4, you're going to see where one of these here is not. So carbon, oxygen, hey, I recognize the big one there. So oxygen is more electro-loving, so it's partially negative. Carbon is partially positive. But wait a minute, what about P and H? We have a little problem here, don't we? The problem is none of them are the big four, so it doesn't say we can't use our electronegativity table, so I think we ought to. So flip back to page 11 and check out what the electronegativity value of phosphorus is. It is 2.1. But wait a minute, that's what hydrogen is. That's not a polar bond, it's non-polar. So we do not put those partial negatives. Let's try another one. Hydrogen and chlorine. Hopefully you recognize chlorine is one of the big four. Okay. Bromine and tellurium. Neither one of those are of the big four. Okay, so what about the bromine and the tellurium one? Without checking that electronegativity chart, my guess is that bromine is going to be a more electronegative element than tellurium. And it's not close enough on the periodic table to make it a polar bond. And if you do check, you'll see that my guesses were right. Bromine is 2.8 and tellurium is 2.1. So this is 2.8, 2.1. Bromine is more electronegative, so it gets the partially negative. You'll see that sulfur and selenium, very similar idea. So I would say sulfur is more polar, or excuse me, more electronegative than the selenium, and it's going to be partially negative. Let's go back to letter D real quick. Again, let's think about this. Bromine is a halogen, so it's a group 17, and it has one fewer shell than tellurium is. So again, that's my general idea of why bromine was going to be more electronegative, and that it's enough to make it a polar bond. All right, so now what? Let's look at the next thing, a dipolar molecule. We are just talking about bonds right now. What about the entire molecule? Again, unfortunately, my picture is not there. Let me draw it in real fast. All right, so again, we were talking about how to figure out if the bonds are polar, but what about the entire molecule? And that's going to be really important in the following chapters, okay? So this is a huge topic, very important you get this. So the molecule itself, you need to have a somewhat negative end and a somewhat positive end, and that's actually defined as a dipole moment. Get used to hearing that. Molecules with a preferential orientation electric field. So notice, again, if this is the positive plate, notice that the partially negative oxygen is oriented itself by the positive plate. The partially positive hydrogens have oriented around the negative plate. That's what that means, okay? So it's very important that you look at two things. You got to look at their symmetry and you need to look at their bond polarity. Okay, so it says all diatomic molecules with a polar covalent bond are going to be dipolar. So any two atom molecules that has a polar covalent bond are going to be dipolar. If they're opposite, or if they're different molecules or different atoms, I'll get it right. If they're different atoms, such as HF, okay, it's a dipolar or it's a diatomic molecule, it has a polar bond, as the whole molecule itself is dipolar. It has two poles, a positive pole and a negative pole. Now it says, what about molecules with polar bonds but no dipole moment? This could be a couple things. It could be linear, radial, or tetrahedral symmetry. That's our next chapter. Don't get unglued about the fact you don't know how to figure out what their shapes are. We'll probably, for this section, just give you the picture of it, and you tell for yourself if it's symmetrical or not. So for example, let me show you these pictures. Actually, you have them in front of you. Let me put them in real quick. Okay, so look what happened here. Carbon dioxide is actually linear. Although the CO bond itself is polar bond, put the whole thing together, it really is a non-polar molecule. If you look at it, it's like a tug of war. Even though this is a polar bond and that's a polar bond, they cancel each other out. Now look at CH4, it's tetrahedral. Although we have two things going here. Each bond is nonpolar. If you look at the electronegativity difference, the bond is going to be a nonpolar bond. And look how perfectly symmetrical it is. If you had this in place of the H's, you know for a fact that fluorine is one of the big four, okay? You know that each bond there is going to be a polar bond, but it's like they all cancel each other out in a sense. So if I do like this, if we're tugging here, 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 they cancel it out and there is no dipole moment. Let's go ahead and turn the page. Okay, so let's look at these pictures first of all. Do they have polar bonds? Well, the answer to the first one is yes, these have polar covalent bonds. We are looking at the carbon-oxygen bonds. Does it have a dipole moment? No dipole moment. Why not? Because they are symmetry. They're symmetrical. They cancel each other out. They have one of each. They don't have both or neither. What about F2? It's linear. The bond itself is a non-polar covalent bond. It has no dipole moment. So it's neither. Okay, so that would have a non-dipole moment. Okay, it's a non-linear, or excuse me, it's a I don't know what I'm trying to say. It's neither. How about letter C? I'm looking at the bonds. The bonds themselves are polar bonds. How do I know? I'm working with chlorine. But is it symmetrical? And the answer is no, it's not. See that lone pair on top of the phosphorus here? It's non-symmetrical. If I were to look here, do these arrows, in a sense, cancel each other out? The answer is no. CH4, the bond is nonpolar. It is perfectly symmetrical, so it has no dipole moment. Okay. Finally, the last part of here is we can actually measure the dipole moment. It actually gives a number to it. I've actually seen no question like this on the AP exam. But in case you're wondering, that mu is your measurement of the dipole moment, is equal to Q times R, where it's the magnitude of the charge, like +1, +2, or whatever, and the distance. And what this calculation is separating the proton from the electron. You multiply these together, and look at your units. That's a capital C for Coulomb, M stands for meters. You get a debye, and so you end up figuring out how many debye's it is. Again, never seen any of that on the AP exam. The ionic character is a percent. You take the measured dipole of the XY bond and then the measured dipole moment of the two different charges times by 100%. Again, never seen that on the AP exam. And I am done with 9.6. Thanks.